Electricity is used on a day-to-day basis, from phones and computers that are used for communication and work, to cars and trains which we use for transportation, primarily using motors. Which brings us to an interesting point, that we sometimes make electricity using motion. This is done using generators, water turbines, and windmills, among other methods. But how are we able to convert between motion and electricity? The key lies in using moving magnets. In this mini-series, we'll use specially designed equipment to experimentally discover quantitative relationships between moving magnets and the electricity they generate. This is a turntable where, as you can see, this is a spinning disk, and we will be using this to perform experiments with electromagnetism. To start with, let's get a hang of how it works and how to set it up. First, you'll notice that there are two wires coming out of it. This is what we'll be using for our sensor to track how fast this disk is spinning, and this wire is what we'll be using to power the motor that's spinning the disk. As for the controller for this turntable setup, we'll be using this device. It has 3 cables that we'll be connecting, one of which will be to an external power source, and that will allow us to control this turntable. First, we're going to take the corresponding cable for the sensor on this controller and connect it to the turntable here. Make sure that the wire colors match. Next, what you're going to do is take a corresponding jack and connect it to the socket wire on this turntable. Next, what we're going to do is take a power source. In this case, we're using a 12-volt brick source to power our controller. So we're going to take this cable and use it to power this jack on the turntable. This will provide the total power that we ever might need to use to turn the disk. And finally, we're going to power the microcontroller itself with a USB Type-C, although you could use a LiPo battery. And when we turn it on, you'll see the screen turn on, and you will also see what is going to be the direction and angular velocity of the turntable. The following controller is an Arduino-based device called the Adafruit Feather ESP32S2. With this device, we're able to manipulate a few factors about this turntable. For instance, if we were to press the top button, we can increase the speed at which the turntable is, which is affecting the angular speed measurement we are getting, known as omega, or in radians per second. Next, if we press the bottom button, we can decrease the speed to create a correspondingly decreased angular velocity omega. And finally, we can even change the direction at which the disk is spinning. For instance, right now it's spinning counterclockwise, but if I press the middle button once, it switches to clockwise. If I press it once more, it stops. If I press it a third time, it'll reset the cycle back at counterclockwise. The number in the right top corner of this screen is the number of revolutions being counted, and every 5 revolutions it updates the angular velocity omega to give us an average of the 5 revolutions. To measure the voltage, we have 2 components at work. The first, the element on the top, is an analog to digital converter. This device will take in the voltage induced by the moving magnet in the coil and amplify it to a visible extent. Then, the other device on the bottom, the ESP32S2, different from the one that's controlling our turntable, will display the voltage on a time and voltage graph, as seen here. The minimum and maximum voltages will be displayed at the bottom and top of the screen as shown. Now, to perform experiments in electromagnetism, we're going to need a magnet. That is why we have this extremely strong neodymium magnet, which we've marked the north pole of by this red dot, and we're going to put it in this holder here right on the turntable. Now, you might be familiar with the experimental setup where if you have a copper coil next to a moving magnet, voltage will be induced. And that's exactly what this device here is for plotting out the voltage induced by a moving magnet. When we start spinning the magnet at a constant rate in front of a copper coil, we notice this produces a sine wave-like voltage on this graph seen here. This is due to the fact that when we're spinning the magnet, this causes a change in the magnetic field that is crossing through the coil. In other words, we're changing the magnetic flux in the coil. And that produces our electromotive force, or EMF. If we start increasing the rate at which the magnet spins, we are increasing the velocity, and this, as seen here, increases the height of this sine wave-like voltage. If we were to decrease the spinning rate of the magnet, we would notice a similar sort of decrease in the sine wave amplitude. What we want to do in this experiment is establish a quantitative relationship between the angular speed of the magnet and the EMF produced by the magnet in the coil. At a motor power throughput of 60, we get an angular speed of approximately 5.5 radians per second, and our maximum induced voltage is 50 millivolts. And if we increase that to a motor power throughput of 90, our angular velocity then changes to approximately 8.5 radians per second, and our maximum EMF turns to approximately 75 millivolts. Then repeat this again for a motor power throughput of around 120, and then our average angular velocity increases to around 12 radians per second, with the maximum EMF being around 105 millivolts. And then we repeat this for 150, and then we get approximately 15.5 radians per second with a maximum EMF of 136 millivolts. Increase this to 180, and then we get approximately 18.5 radians per second with a maximum EMF of 165 millivolts. And then finally, for one big jump to a motor throughput of 240, we get an angular speed of around 25.5 radians per second, and that leads us to a maximum EMF of 220 to 225 millivolts. When we plot our data points marked in red X's on a graph, we see that there is a very close to, if not exactly, linear relationship between the EMF in a coil and the angular speed at which the magnet rotates. This suggests that EMF is directly proportional to the angular velocity. Michael Faraday got similar results when he performed his own experiments, indicating that the EMF produced in a coil would be directly proportional to the speed at which a magnetic field passed by said coil. Thus, through our own efforts, we have managed to quantitatively verify and reproduce the results and theories that Faraday had put forth centuries before. We have discovered Faraday's law on our own terms.